It's reasonable to say that the universe still keeps a few secrets from us. We've measured the ages of stars, weighed galaxies, mapped the afterglow of the Big Bang, and yet the grandest question on the table is embarrassingly simple. Why is space growing apart, and why is it doing so faster and faster? For over a century, we assumed that gravity would act as a brake on the expansion that began in that first bright moment. But when astronomers used dying stars as cosmic mileposts, little standard candles flaring and fading with remarkable regularity, the picture shifted. The distances implied by those explosions told us that the fabric of space isn't merely coasting, it's pressing the accelerator. We gave that behavior a name, dark energy, because naming a mystery at least lets you talk about it over tea. The name tells you very little. It is not dark in the sense of a color, nor energy in the sense of electricity humming through a wire. It is simply a label for the observation that on the largest scales, empty space behaves as if it carries a gentle pressure. Add more space, and by the look of it, you get more of this pressure. That sounds like getting something for nothing, which ought to make any sensible physicist nervous, and yet the measurements persist. So what might it be? There are two broad ways to think about it. One is that there is genuinely new stuff out there, perhaps a field pervading space that we've not yet pinned down in a particle detector. The other is more radical, perhaps our theory of gravity is incomplete on cosmic scales. Both camps are hard at work. We design experiments in quiet laboratories, cooling atoms to a whisper, searching for forces that hide in dense environments and reveal themselves in a vacuum. We also build surveys that map the positions of millions of galaxies across billions of light years, using the growth of structure in the universe as a kind of seismograph for the physics of expansion. The more detail we gather, the fewer places a wrong idea can hide. There is a kind of modesty to all this. Scientists often sound confident in documentaries, but the truth is more beautiful than certainty. We stand beneath a sky stitched with 100,000 million suns, and we admit quite openly that we don't yet know what drives most of its behavior. The thrill lies in the not knowing, because ignorance, when precisely defined, becomes a compass. It points to better telescopes, cleaner measurements, tighter theories. And ideas that presently fit the data will be thrown away as new maps arrive. That is the rhythm of discovery. Now, whilst cosmic acceleration is the quiet, persistent puzzle of the age, some mysteries are brash and immediate. Consider a star so dense that a spoonful would outweigh a mountain, and so magnetic that it could rip the very electrons from your atoms if you were foolish enough to wander close. We call these corpses of massive stars neutron stars. Their more temperamental cousins are magnetars. They're no larger across than a modest city, yet they are born in the death throes of suns many times heavier than our own. Gravity wins the final battle, crushing protons and electrons together until the core becomes a single degenerate sea of neutrons. It's easy to say those words quickly, sea of neutrons, but the reality is difficult to imagine. If you were to drop a marshmallow, an odd choice for fieldwork but a useful image, onto such a surface, the energy released would rival that of a nuclear weapon. The crust would accept your offering without ceremony. The interior hardly notices. There is no softness left in matter here. And yet from that hardness comes a different kind of grace, beams of radio light sweeping the sky as the star spins a lighthouse in deep time. Those are pulsars. In some systems, the spin is so stable that you can set your watch by it. In others, it races along like a kitchen blender, hundreds of turns each second, the entire star rotating as one. Why are some of these objects so extraordinarily magnetic? We have reasonable sketches. As the core of a massive star collapses, magnetic field lines are dragged inward and intensified, rather like tightening the coils of an invisible spring. Add to that the peculiar electrical behavior of matter at such densities and temperatures, and you begin to cook up fields with strengths that beg comparison, billions of times stronger than anything we can achieve in our laboratories. But if I said we fully understood the recipe, I'd be overstating it. This is frontier territory where observation leads theory by the hand. Sometimes two neutron stars find themselves bound together, whirling in a doomed dance. With each orbit, they lose a whisper of energy to ripples in space-time gravitational waves, and the separation shrinks. Eventually, they merge. In that moment, the universe rings like a struck bell. The waves race outward at the speed of light, and if we are lucky and listening, our detectors twitch. The aftermath can be a black hole, or for a brief, violent interlude, a remnant that is even more magnetic than before, a magnetar born in fire. These collisions forge heavy elements, gold, platinum metals that end up in rings in circuits in the dust beneath your fingernails. In a literal sense, parts of you are minted in the funerals of stars. I find that a helpful way to think about astronomy, not as a study of distant curiosities, but as a genealogy. We are related to these objects. The mystery of dark energy governs the architecture of the vast web of galaxies from which our Milky Way was drawn. The physics of dying stars populates the periodic table in your bones. To stand under the night sky is to attend a family reunion. Now, there is another idea that sits further out on the edge, an idea that polite company once dismissed with a smile and a change of subject. It is the suggestion that the word universe may be parochial, that what we call the universe is a region of a larger whole, and that other regions may exist with histories of their own. You can arrive at this thought from a few directions. One comes from quantum theory, which says that on the tiniest scales, nature behaves like a musician who plays many notes at once. When we measure, we hear one note. The mathematics, though, seems to allow that other outcomes continue to exist elsewhere in the grand wave of possibility. Another route is cosmological inflation, a simple idea about a brief burst of expansion in the first fraction of a second. In many versions, inflation does not end everywhere at once. It leaves behind bubbles, each with its own hot Big Bang and perhaps its own local laws. Do I believe in a multiverse? I think it's fair to say I take it seriously. But belief isn't the point here. Evidence is. Quantum theory is tested every day, but the interpretation that multiplies worlds remains a matter of taste unless it makes predictions we can check. Inflation, on the other hand, has left patterns in the sky, the distribution of galaxies, the texture of the cosmic microwave background that are compatible with the basic picture. Whether the more exuberant versions, the ones that spawn many pocket universes, are true is another question entirely. I'd be delighted to be wrong about my preferences, provided nature is right. All of these threads, the hidden pressure of empty space, the ferocious calm of neutron stars, the speculative grandeur of multiple universes, belong to the same human enterprise. We look up, we measure, we argue politely, we throw away cherished ideas when the data demands it, and we keep our language honest. We don't know is not a defeat. It is the beginning of the next adventure. In a moment, I want to follow one such thread down to a single world, a giant planet whose polar skies are lit by permanent curtains of light. Those aurorae pulse with the patience of a metronome, and at their heart lies a form of hydrogen that behaves like a metal ocean. To understand that is to understand how a planet can become a generator and why its moons add their voices to the song. Let's go there. When you look out towards the outer planets on a winter night, the sky offers you a cold lantern hung low above the horizon. Through a small telescope, you might see a tiny disk with attendant points of light, and you could be forgiven for thinking it a neat clockwork arrangement. It is anything but. That world is a storm in slow motion. Its poles glow with curtains of emerald and violet. Its belly is a theatre of endless weather. And deep within, beneath the belts and zones and the famous scar we call the Great Red Spot, there is a sea that is not water, not rock, not any ordinary stuff at all, but hydrogen so tightly pressed by gravity that the atoms surrender and the electrons drift freely, turning the heart of a planet into a metal ocean. A metal ocean is a delicate phrase for something colossal. Imagine a globe the size of a small star's ghost, spinning patiently, its inner layers moving like a conductor's hand through a choir of charges. Motion in a conducting fluid creates a dynamo. The dynamo creates a magnetic field. The field reaches out like invisible weather, shaping charged particles, guiding them into spirals and arcs. The result is a magnetosphere, so large that were it visible to your eyes, it would dwarf the apparent size of the sunday. The solar wind, that ceaseless breath from our star, crashes against it and flows around like a river, parting around a stone, except the stone is alive with current. From the outside, you see the beauty ovals of auroral light around both poles, bright knots that flicker and drift. From the inside, the microscopic, the practical, the story is pure electricity. Electrons and ions are accelerated along field lines. They slam into the upper atmosphere and set the gases singing. You can, if you like, think of the whole planet as a great instrument with the strings stretched from pole to pole and the bow drawn by sunlight and moons. The notes ring in radio as well as light. Even on Earth, you can sometimes catch the crackle of those emissions with the right aerial on the right night, a whisper from a distant storm. The moons matter. One in particular refuses to be quiet. Io is a small tortured sphere close to its parent, kneaded by tides until its interior is molten and its surface erupts. Volcanoes throw fountains of sulfur and oxygen into space. Those atoms and ions are swept up by the planet's magnetic field and corralled into a torus, a smoke ring of matter that co-rotates with the planet. Now take a conducting moon moving through a magnetic field. By the rules of electromagnetism, you get a current. A circuit is completed along the magnetic lines into the planet's atmosphere. The aurora brightens where those lines meet the polar sky, an electric footprint of a moon drawn upon a planet. It is a simple idea taught in school laboratories, written here on a scale that makes the mind lean and steady itself. Another moon carries a quieter marvel. Ganymede is large enough to be a small planet in its own right, and it holds an internal magnetic field. It is, as far as we know, the only moon to do so. The result is a magnetosphere nested within a larger magnetosphere, a Russian doll of fields. Watch how the smaller bubble rocks in the larger wind, and you can deduce the presence of a hidden ocean beneath the ice, because a salty ocean resists the changing field differently from plain rock. In this way, the behavior of aurora becomes a method of plumbing a world you cannot yet reach. Return your gaze to the cloud tops, and you will see order and chaos interleaved. Bands of pale and bands of dark streaming east and west in alternating jets. Threaded through them are vortices like open mouths. The great red spot, though gentler now than in past centuries, is still a storm wider than the Earth, a cyclone that has been spinning for longer than any human nation. We have flown craft past and through this system, and the measurements tell us the winds dive deep, that the colours are tied to chemistry coaxed into being by sunlight and lightning, and by the upwelling and downwelling of gases richer or poorer in certain elements. If you could float a small balloon there, it would ride a stairway of speeds and temperatures sampling a laboratory we did not build, but are blessed to visit with mathematics and courage. It is tempting amid all this grandeur to think of the giant as an outlier, as a showpiece that stands apart from us. It is not. The same physics makes Earth a home. A smaller, slower dynamo churns in our planet's liquid iron outer core, raising a magnetic field that shields our atmosphere from the worst of the sun's temper. Our aurora are the domestic version of those polar curtains. Our radio crackles and our compass needles nod for the same reasons. The language of fields and flows set down in the 19th century by Faraday and Maxwell turns out to be a story written across the solar system. Learn to read it here and you will recognize the script on worlds around other stars. Now tilt your head and step sideways through the rings of a neighbor. Saturn is another giant, paler, calmer to the eye. Its rings look solid in photographs, as though a craftsman had shaved a disc from a block of ivory. Stand on the night side and you would see they are anything but solid. Millions upon millions of ice fragments from dust to boulders wheel in a flattened swarm. The rings sing too, though most of us will never hear it. They respond to the planet's interior in subtle ways. Waves ripple through them when deep oscillations, standing modes in the planet's body tug at their orbits. In that sense, the rings are a seismograph. Read their patterns correctly, and you can infer the structure of the world they encircle. It is a tender thought, a planet speaking through snow and shadow. There is rain here as well, though not the kind that dampens streets. Charged water molecules fall from the rings into the planet's atmosphere, a chemical drizzle that leaves its mark on the ionosphere and shifts the brightness of the aurora. And from a small moon, Enceladus, jets of vapor and ice grains burst from fractures near the South Pole, feeding a faint outer ring. Inside those grains we find salts and organics and the signature of warm water hinting at hydrothermal vents under an ice shell. In such places on Earth, life blooms in the dark, nourished by chemistry rather than sunlight. It is not foolish to wonder whether similar engines churn beneath alien ice. We do not have the answer. That is the adventure to come. From the outside, these are pretty scenes, arcs of light. At the poles, narrow rings catching the sun, pale storms turning in silence. From the inside, they are opportunities to test ideas to destruction. Does our theory of how dynamos work match the depth of the winds? Do our equations for magnetized plasmas reproduce the shape of the auroral ovals? Do our models for ring particles colliding and sticking and shattering explain the unexpected sharpness of edges and the longevity of gaps? If the answer is no, we change the theory. If the answer is yes, we press further, because agreement on yesterday's measurement is no guarantee of tomorrow's truth. I like to think of the giants as teachers of patience. Their weather changes on human timescales, but their deep structures evolve on spans far longer than a single career. You can devote a life to a single current, a single band, a single set of waves in a ring and never exhaust it. That is not a counsel of despair. It is an invitation to join a very long conversation. We inherit observations from those who stared up with brass instruments and glass lenses. We pass on data gathered by robots that thread the belts and brave the radiation. Somewhere down the line, someone will understand a detail we have only just noticed, and when they do, the sky will open a little wider for everyone. In a moment, I want to leave the splendor of giants and turn to something more fragile atmospheres that are not our own, slipping across the faces of distant suns. With nothing more than starlight filtered through alien air, we can begin to read the chemistry of worlds we will never visit and ask a question that is as old as wonder. What would it be like to stand on another shore and breathe? If you want to take the measure of a world you will never visit, you begin with a shadow. A planet crosses the face of its star, and for a few hours the light dips by a fraction. That small eclipse is not merely a tick on a graph, it is an invitation. A thread of starlight passes through the planet's air, if it has any, and arrives at our telescopes carrying the faintest imprint of that sky. Split the light into its colours, and you find tiny bites taken out lines where particular atoms and molecules have robbed the beam of a little brightness. Read those lines and you read weather from across the void. It sounds like magic, but it is patient craft. Sodium leaves a pair of dark notches, water vapour, a comb of features in the infrared methane and carbon dioxide, their own signatures. And it isn't only chemistry. By watching how the depth of the transit changes at different colours, we can sketch the scale height of the atmosphere, the way pressure drops with altitude, and so infer temperature and gravity. In a handful of cases, we can even see the planet's dayside brighten and fade as it whirls around the hot face, turning towards us and away again. That rhythmic glow of phase curve tells us where heat is piling up and how fast winds are carrying it around the globe. Some of these worlds are so close to their suns that a year lasts only a few days and the dayside is hot enough to melt rock. We called them hot Jupiters when they were first found because the name made us feel better about the absurdity. Their clouds may be made of silicates and metals, their raindrops more like glass than water. The winds scream from the day to the night at thousands of miles an hour, and yet within the chaos there is intelligible order. The peak brightness does not always line up with the point of closest approach. It shifts, betraying the direction and strength of the high-altitude jet. It is meteorology writ in fire. Other planets are quieter. There are swathes of small worlds between Earth and Neptune in size super-Earths and sub-Neptunes, the language still settling that seem to carry thin veils of hydrogen or thicker cloaks of heavier gases. Some may hide global oceans beneath atmospheres swollen by heat. A few sit in the temperate band around their stars, where water, that wonderfully fussy molecule, can be liquid on a rocky surface. Habitable zone is a generous phrase. It tells you where a lake could exist, not whether it does. Still, it is a map, and maps are where journeys begin. Even air can escape. Helium, being light and shy, can flee a hot atmosphere under the encouragement of the star's radiation, leaving a faint tail comet-like that we can detect in the right colour of light. Picture a world spilling itself into space layer by layer over eons. The shape of the loss tells you about the strength of the star's temper and the planet's gravity. In that sense, we are watching not just skies but histories, how a young system baptizes its planets in heat and wind, and how, if they are fortunate, they settle into quieter adulthood. The stars themselves complicate and enrich the story. Many of the worlds we can best study circle small red suns. Those stars are long-lived and numerous good qualities for the emergence of complexity, but they can also be feisty, throwing flares and bathing their close-in planets in radiation. A magnetic field might shield a planet. A thick atmosphere might heal. Oceans beneath ice might ignore the storms above. It's reasonable to say we don't yet know how often temperate air survives in such company, and that not knowing is turning into a program of careful monitoring. We are, in effect, learning the personalities of stars because climate begins there. What about life? It's a question to be asked softly. Light, filtered through alien air, might in time show combinations of gases that are hard to explain without biology, oxygen alongside methane, for example, or unexpected imbalances that require a vigorous source. But planets are good chemists, and nature is inventive. There are false positives and false negatives waiting to ambush the overeager. So the rule for now is caution. We build a case molecule by molecule, season by season, world by world, until a pattern emerges that does not yield to geology or photochemistry. That will be a day to savour and to doubt and to test again. Even without that revolution, there is a quiet delight in reading a sky from a fleck of light. The first time you watch the spectrum of a distant planet flatten and deepen, where water should be, you feel a small wobble in your understanding of distance. The star may be dozens or hundreds of light years away, and yet here you are weighing the steam in the air of a world you cannot name without a catalogue number. Stand in a dark garden on a clear night, point to a star, and say with complete honesty, there is a place with sunsets of a colour we can predict. That is not poetry, that is measurement. All of this is new, and yet part of an older tradition. Astronomers have always been extravagant minimalists. They ask simple questions of meager photons and extract empires of knowledge. We did it with the planets of our own system, watching the wobble of Mars to test the law of gravitation. We did it with the light of galaxies to learn that space itself expands. And now we are doing it with the atmospheres of distant worlds to sketch a catalogue of climates. The joy lies not only in the answers, but in the method, careful, transparent, slow and open to being wrong. You can build a civilization on that. If we are fortunate and persistent, the next decades will move from air to surface. The glint of starlight off an alien ocean forward scattering from a billion ripples would be a clue that water stands under a sky. The seasonal reddening of continents as vegetation blooms and retreats is an audacious dream, but one can outline the path from here to there. Bigger mirrors, cleaner instruments, bolder surveys. And as we press on, the question of company will return, because it always does. Are we an exception, a local curiosity on the shores of a single lucky world? Or does life given time and chemistry emerge wherever it can? For the moment the universe is quiet. We detect no unambiguous beacons, no engineered artifacts, no signatures that demand an intelligence. That quiet can feel lonely, or it can feel like permission. It says explore. Fill the silence with understanding. And never confuse a lack of shouting with a lack of neighbours. If they exist, they may be patient, they may be rare, they may be everywhere and very far away. The only honest position is to keep listening in as many ways as we can invent. Light is the oldest instrument in that listening, but it is no longer the only one. Space and time themselves can carry a tune. When heavy objects move with violence, they shake the fabric and send waves racing across the cosmos. We have learned at last to feel those ripples in the dark with machines of exquisite delicacy. Before we follow them, though, there is one more piece to place on the board. The grave of a massive star, and the door it opens. Not outwards but in. Let's step towards the edge where time itself begins to behave strangely and see how a black hole can make the whole universe ring. The story of a black hole begins with a very ordinary act of gravity falling. A massive star runs out of fuel in its core, and the delicate balance that held it up, outward pressure from hot gas and inward pull from its own weight, crumbles. The outer layers rush down, meet a rebounding shock, and a supernova flings the star's skin into space. But the heart keeps falling. It passes the point where atoms can help then, the point where even neutrons, those sturdy little bricks of matter, can bear the strain. Down it goes, and the mathematics says there is no longer a surface to hit. Space and time themselves become the stage on which the collapse continues. From the outside we see a boundary form, a sphere from which not even light can escape. That is the event horizon. It's a curious name because nothing particularly dramatic happens at the horizon if you are the one falling. You cross it without fanfare. There are no flames, no rocks, no walls to scrape a hand against. Locally, Einstein promises physics is boring and familiar, but for a distant observer, your passage is never completed. Light from your last moments is stretched to redder and redder colours by gravity. Clocks appear to slow and then freeze. Your final wave lingers fainter and fainter as though time has congealed on the brink. Both views are honest, and both are true because time is not absolute. It is threaded through space in different ways for different paths. Now stare not at the brink, but just beyond it into the region where the orbit of light itself is bent into a tight circle. Their photons loop once, twice, perhaps thrice before escaping. That repeated skimming builds a bright ring if you have a telescope sharp enough. We have at last glimpsed that ring around a giant in another galaxy and around the dark heart of our own. It is not a photograph of a surface, but a portrait of geometry, the outline of a shadow cast by gravity on light. The ring is thicker on one side because the matter around the hole is orbiting and the approaching flow adds a little energy to the light, brightening it. Even beauty here obeys the laws of motion. Black holes are not merely eaters, they can be engines. When matter falls in with a bit of spin and a bit of order, it forms a disk that heats and shines across the spectrum. Magnetic fields thread the disk, and near the hole twist into ropes. Along those ropes, particles are hurled outwards at nearly the speed of light, in narrow jets that can lance through a galaxy, stirring and shaping clouds of gas. Paradoxically, by denying their surroundings the dignity of rest, black holes help write the next chapter of star formation. In that sense, they are gardeners as well as graveyards, pruning, stirring and feeding the cycles that make new suns. But perhaps the most exquisite thing a black hole does for us is play music, the music of gravity. When two of them orbit each other, they radiate energy as ripples in space-time. The orbit shrinks, the pace quickens, the pitch of the wave rises. At the final instant when their horizons touch and merge, the signal peaks and then softens into a dying tone as the new, larger whole settles vibrating in a set of pure notes. That last part ring down is not poetry. It is a measurable chorus of frequencies determined only by the mass and the spin of the final whole. The theory says this, and the detectors have begun to hear it. What does it take to listen? Imagine a ruler made of light 4 kilometers long, laid out along 2 arms at right angles. At each end sits a mirror polished to absurd perfection. A laser beam is split, sent down both arms, reflected and brought back together. If a gravitational wave passes, it stretches one arm while squeezing the other by a fraction of a fraction of a fraction of a proton's width, and the light's pattern of bright and dark fringes shifts. That shift is the whisper we call a detection. To notice it at all, we must quieten the world, isolate the mirrors from ground tremors, hush the rumble of traffic and the drag of thermal noise. It is a triumph of engineering as much as physics, a cathedral of precision, erected for a single purpose: to feel space-time ring when heavy objects collide in the dark. The first time that tremor arrived, it was brief, less than a second of rising tone. But within that instant lay a tale of 2 black holes spiraling together, far beyond our galaxy, their mass converted into gravitational radiation at a rate that briefly outshone the starlight of the entire visible universe. Since then, the catalogue has grown each entry a new test of ideas. We can ask whether the waveform matches the predictions of Einstein's theory with pedantic severity. Thus far it does. We can check whether the final ring-down note is exactly what a black hole should sing, or whether there are hints of something else, some exotic alternative. Thus far it is a pure, austere song. There is more. Sometimes a neutron star is in the dance, and then the light show joins the music. As the smaller body is torn apart in the last orbits, hot debris glows across the spectrum, and radioactive elements freshly forged in the chaos decay, painting a kaleidoscope that fades over days. If you can catch both the gravitational wave and the light, you have a standard siren, a way to measure distance directly from the waveform, and a redshift from the light. Put enough of these rulers into your cosmic map, and you can trace the expansion of the universe without relying on any single ladder of calibrations. That is a quiet revolution in a field obsessed with ways of knowing how far away things are. And yet, even as the detectors confirm old ideas, the holes themselves throw up new conundrums. Stephen Hawking taught us to take quantum mechanics seriously at the horizon. When you add the jitter of the vacuum to the serene geometry, the math suggests a black hole is not entirely black. It bleeds energy slowly, as if space near the horizon has a temperature. Over fantastically long times, the whole would evaporate. But then what of the information about what went in quantum theory abhors the loss of information? General relativity, left to its own devices, doesn't mind at all. The tension is crisp. You can dress it in metaphors, books burned, stories erased, but the beating heart of the problem is simply this: 2 trusted pillars of physics quarrel mildly at the edge of a black hole. Our job is to mediate. Many clever proposals circulate. Some physicists imagine that the information is smeared on the horizon, like ink on paper, to be read in principle by the outgoing radiation. Others invent soft hair, delicate imprints left on the gravitational field that remember what fell in. Still, others flirt with firewalls and radical rewrites of the interior. I think it's fair to say that none of these ideas has yet earned the right to be called the answer. That is fine. The frontier of knowledge is supposed to be untidy. It is where graduate students sharpen their pencils and careers are forged in the agreeable heat of argument. Observation will help. The giant telescopes that image shadows will sharpen. Gravitational wave observatories will become more sensitive. Networks on the ground will be joined by instruments in space, listening to lower notes, the bass lines of colossal mergers. Out there in the long wavelength, supermassive black holes, the monsters at the centers of galaxies, will swirl together over months and years, and we will watch their courtships in slow motion. We will time the pulses of dead stars across the Milky Way and notice in the tiny irregularities the passing weight of waves from distant encounters. When those data arrive, some hypotheses will breathe easier and others will vanish politely. Why spend such care on these austere creatures? Because black holes teach us what cannot be otherwise. They are, in a lovely phrase, the hydrogen atoms of gravity, the simplest non-trivial objects in the theory, and so the surest guides to its limits. If you claim a new law of nature, it must make sense at a horizon. If you propose a modification to space-time, it must sing the same ring down that our machines hear or explain. Why not, in a way that can be checked? In that way, the darkness is not a retreat from knowledge, but a proving ground for it. In a moment, I want to turn from the cold elegance of these beasts to something warmer and stranger, the origin of time's arrow. Why does the future feel different from the past? Why does a cup shatter but not leap back together again? Black holes hide the answer in their entropy, that measure of disorder which for them is curiously tied to area rather than the volume. Follow that thread and it leads out of the abyss and into kitchens, clouds, and the unfolding of life itself. Let's step from the event horizon to your breakfast table and see how the same mathematics links the two. If you want to understand why the future feels different from the past, you could do worse than watch steam curl from a kettle. The vapor spreads, it never gathers itself back up and dives into the spout. A wine glass falls and shatters, it does not leap from the floor and reassemble in your hand. We say time has an arrow and the direction is chosen by a law, both simple and profound. Left to themselves, things tend to move from tidy to untidy, from ordered to disordered. We call that drift entropy. You can define it in equations, but there's a friendlier picture. Think of the universe as a library. An ordered shelf books upright in sequence corresponds to a small number of arrangements. A messy heap has many more. If you jostle the shelf at random, you are more likely to end with a heap because there are more heaps available. Now bring a black hole back onto the stage. Jacob Bekenstein and Stephen Hawking showed us that these objects, which seem so spare and elegant, are in fact champions of disorder. Their entropy is not proportional to how much volume is trapped inside the horizon, which would be the intuitive guess, but to the area of the horizon itself. That is astonishing. The most economical summary a black hole offers of everything it has swallowed is painted on its surface. The bigger the area, the more ways the interior could be arranged while looking identical from the outside. Entropy then is not mere mess, it is a count of invisible possibilities. If a black hole can have a temperature and an entropy, it belongs to the same family as kettles and cups. That is helpful because it links the ground with the familiar. When you boil water, the heat flows from a hotter place to a cooler one until everything settles. When a black hole sits in a universe filled with radiation cooler than the feeble warmth at its horizon, it will in the long run radiate away. The second law, the rule about the arrow, survives the journey from your kitchen to the edge of time. So why did the arrow ever get a chance to start? If the natural tendency is from tidy to untidy, our world must have been impressively tidy to begin with. It was. Look at the oldest light, we can see the afterglow of the hot early universe that now washes over us as a faint microwave hiss. It is astonishingly smooth. There are tiny ripples, just enough to seed galaxies, but taken as a whole, the young cosmos is a portrait of order, temperature, and density almost the same everywhere. From such a neat beginning, there was only one direction for entropy to go upward, and so time as we experience it acquired a sense of flow. You might object quite reasonably that uniformity is not obviously order. A deck of cards sorted by suit and rank is ordered. A deck where every card is identical is dull, but is it ordered? The key is gravity. In a gas without gravity, the uniform spread is the most disordered state molecules everywhere, no patterns. But in a universe where matter attracts matter, uniformity is precarious. The most disordered outcome for a self-gravitating medium is clumpiness stars, then black holes, then if you wait long enough, larger and larger holes. The early smoothness is therefore special. It's the kind of special that demands an explanation. Several ideas compete politely. One proposes that in its first instant, the universe underwent a brief burst of ferocious expansion. That stretching has the pleasant side effect of ironing away wrinkles. Whatever was happening in our patch is blown up until its roughness is smoothed beneath the scale of our view. Another more geometric thought dear to Roger Penrose is that the very early universe had vanishingly little of a particular kind of gravitational disorder, the kind that would later show itself in tangled gravitational fields and black holes. In that telling, the arrow begins not because of the gas and the light, but because the geometry itself was in a highly constrained state. I think it's fair to say we don't yet know which of these sketches, if either, is the picture on the box. That is the delight. The microwave sky keeps whispering clues, and we keep building instruments that can hear them more clearly. Whatever the ultimate origin, the practical consequence of the arrow is this complexity becomes possible. A star forms from a cloud by falling inward, which releases gravitational energy. That energy leaks away as light and heat into the wider universe. The star is a local engine of order, powered by a global slide towards disorder. On Earth, sunlight arrives in neat packets of high-quality energy and departs as a fuzz of lower-quality heat into the deep sky. That downhill flow pays for everything: delicate weather, rivers, chemistry cells that eat and divide and remember. Life does not defy the second law, it dances to it. It takes a small portion of the grand descent, and for a while builds islands of pattern that can copy themselves. There is a good sentence to carry in your pocket: to make a thing that lasts for a time, you must pay entropy elsewhere. The great red spot pays its rent into the belts and zones and the space beyond. A rainforest pays its rent into the warm air that drifts to the night. Your own thoughts are paid for by the oxidation of sugars and the faint rise in the temperature of the room. That is neither bleak nor mechanical. It is the most generous arrangement imaginable, a universe in which the general tendency to disorder creates a slope down which water and light can run, carving out structures as they go. The oddest part of the whole business is that the mathematics, the strict laws, are reversible. The microscopic rules for atoms and fields care nothing for yesterday or tomorrow. If you were to film a gas of ideal particles bumping around and play the film backwards, the equations would nod in approval. The arrow creeps in when you admit that you cannot and need not track every detail. You smear your description, ever so slightly coarse graining we call it, and suddenly the difference between neat and messy reappears. This is not cheating, it is honesty. No brain, no instrument, no galaxy can keep track of all the microscopic coordinates. By accepting that we recover the world, we actually live in the world of kettles and clouds and memories that point one way. Black holes illustrate this honesty with uncomfortable clarity. The horizon hides details. You cannot even in principle read out a complete ledger of what fell in by watching what comes out, at least not with our present understanding. That enforced coarse graining is why the area measures entropy so well. The edge encodes what you are allowed to know. The inside may be rich and particular, but to the outside it is all beautifully the same. If you want a parable about knowledge and humility, there it is. Nature reminding us that some information is not ours to keep tidy. I find it comforting that the arrow born in the first light reaches all the way to our kitchens and our conversations. It ties the fall of a glass to the growth of galaxies and the warmth of tea to the slow dying of black holes. It sets the pace of aging and the redirection of books, and it marks our moment as species clever enough to notice the slope, to ride it respectfully, and to ask where it began. In a moment, let's follow that wandering back to the oldest snapshot we possess, the faint glow that fills the sky in every direction, the afterglow of the hot beginning. In its tiny mottling lies a map of how structure took shape, and if we are subtle hints about what came before the page on which the story begins. Walk outside on a clear night, look anywhere you like, and you are staring not only at stars, but at a faint ancient glow that fills the sky in every direction. We cannot see it with our eyes. It hums at wavelengths far longer than red light. But when we build instruments tuned to those soft colours and lift them above the murk of our own air, the whole firmament lights up with a gentle hiss. This is the afterglow of the hot beginning, the cosmic microwave background. It is the oldest light we can touch, released when the universe had cooled enough for free electrons to find protons and settle into atoms. Before that moment, light could not travel far without being scattered. After it, the cosmos became transparent, and the first photograph was taken not by a camera, but by reality itself. At first glance, the picture is boring. The glow is almost the same in all directions. The temperature is astonishingly uniform. And yet, on top of that, sameness sit tiny speckles, ripples only a few parts in 100,000. Those freckles are everything. Where the glow is a fraction warmer, the density was a fraction higher. Where it is cooler, a fraction lower. In those slight differences lay the seeds of every galaxy, every star, every leaf and lighthouse and radio song that would one day exist. If you ever doubt that small things matter, consider that the entire drama of cosmic structure is written on a background that barely deviates from perfect smoothness. How did the freckles arise? Wind the clock back to a time when the universe was a hot, thick soup of light and matter tightly coupled together. Photons pushed on the plasma, and the plasma pushed back. The whole mix rang like a bell. Compression raised the temperature, and pressure, rarefaction, lowered them. Sound waves, literal sound, though not through air, rippled outwards at a prodigious pace. When the atoms formed and the light broke free, those frozen waves were stamped into the pattern of the sky. If you plot the strength of ripples against their size, you do not get a featureless blur. You get peaks and troughs, a harmony of preferred scales. We have measured that harmony with delightful precision. It is not a flourish. It is the unmistakable signature of a young universe that behaved as a simple fluid, obeying simple rules. The light carries more than temperature. Its electric and magnetic fields have orientations that can be teased apart into elegant patterns, polarization. Some of that polarization arises because the ripples in density scatter light in a preferred way, imprinting neat, curl-free designs we call E-modes. There is in principle another pattern, delicate swirls called B-modes, born either when the light is deflected by the gravitational pull of intervening matter, or more thrillingly, when the fabric itself was shaking at the very beginning. We have seen the lensing contribution clearly. The primordial swirls remain a quarry for the patient. If we were to find them beyond doubt, they would be a whisper from the first sliver of a second, a hint that space expanded with a ferocity called inflation. I think it is fair to say the hunt is honest and ongoing. Between us and that ancient wallpaper lies all the matter in the universe, and its gravity bends the paths of the photons, slightly smearing and shearing the patterns. That distortion gravitational lensing turns the background into a subtle map of the invisible scaffolding on which galaxies are strung. Read it well, and you learn how clumpy the cosmos has become by now, which in turn tests our picture of how quickly structure should grow. It is a rather satisfying chain. The oldest light tells you the rules. The lensed light tells you how those rules have played out. The same early sound waves that sculpted the sky also left their mark on the later distribution of galaxies. Imagine each overdense patch sending out a spherical pressure wave. When the universe was young, a ripple racing through the plasma until the atoms formed and the push of light switched off. Where those ripples stalled, a preferred separation was imprinted. Billions of years later, when you measure how often galaxy pairs sit at different distances, you find a gentle bump at a characteristic scale. Astronomers call this pattern baryon acoustic oscillations. It is a mouthful, so let us simply say it is a standard ruler. Measure how large that subtle crest appears at different epochs, and you can trace how the expansion has sped and slowed. Place those measurements alongside the ancient sky and alongside the stories told by supernovae, and you begin to triangulate the behavior of the whole. You may have heard that the universe is having a small family disagreement about its rate of expansion today. One camp builds a ladder from nearby stars to nearby supernovae to more distant ones and arrives at a particular answer. Another camp reads the early sky, the peaks and troughs, and the delicate lensing folds in the standard model of particle physics and predicts a value for the present that is a little lower. The difference is modest, mere percentage points, but it is persistent. It may be that some of our calibrations are slightly biased. It may be that new physics peeks through the gap, a slight twist in the behavior of dark energy, an additional light relic in the early plasma, a nuance in how gravity plays on very large scales. I emphasize we do not know. What we do know is that both sides are working with sincerity and care. The tension is not a crisis, it is a gift, because well-posed puzzles drive better measurements and braver ideas. From the freckles in the first light to the filaments on which galaxies hang is a long road, but the map is clearer each year. Simulations that begin with those tiny initial ripples and the simple pull of gravity grow a web that looks uncannily like the one we observe. Vast strands of dark matter, unseen but inferred by their gravitational hand, draw in gas. The gas cools, falls into halos, ignites into stars, and throws winds that heat and stir the outskirts. Small halos merge to make larger ones. In some places, the collapse goes so far that black holes anchor the centers and carve out jets that can throttle star birth in a kind of feedback. None of this is ad hoc flourish. It is the natural consequence of starting conditions, so plain you can write them on a postcard. Dark matter then. Another label, another honest confession. We can measure its gravitational pull. We can map its distribution statistically. We can watch galaxies and clusters behave in ways that cry out for more mass than the light alone reveals. Yet we have not caught the particle, if it is a particle in the act. Underground chambers wait in the quiet earth for the faintest tap. Colliders search for missing energy. Astrophysical observations place tighter collars on what it might be and what it cannot be. A century ago, we assumed the stars were the whole story. Now we think most of the matter is something else entirely. It is a lovely lesson in humility written large across the heavens. Stand back from the detail for a moment and take the whole scene in the nearly featureless infant glow, the tiny ripples etched upon it, the slow growth of structure, the rise of galaxies and the weather of their stars, the heavy elements forged and thrown into space, the assembly of rocky worlds with seas and skies, the quiet that allows chemistry to play and thought to wake. The arrow of time has run downhill from neatness to richness. The marvel is not that disorder grows, but that in the eddies and backwaters of that growth, islands form where complexity is possible. We are one such island. Our telescopes are the tide pools in which the ocean is reflected. In a moment, let's leave the oldest light and dive into a different kind of dawn. The first stars and galaxies, the age when the universe switched the lights back on. How did darkness end? What were the first beacons like, and how did their young fury tear the fog from the sky and make space transparent once more? There was a time when the universe was dark. Not empty, never that, but without beacons. The hot beginning faded atoms formed, and the glow slipped to longer and softer colours until it became a chill whisper. Hydrogen and helium, the simplest gases, drifted through expanding space. Gravity had a long, quiet job to do. Seeded by those tiny ripples in the first light matter, gathered into filaments and knots. In the densest knots, gas cooled, collapsed, and somewhere, sometime, one cloud became the first star. It switched on, and the universe, which had been patient for hundreds of millions of years, had its dawn. We think those first stars were different from the ones we know. With almost no heavy elements, no carbon, oxygen, silicon, the gas could not radiate its heat away quite so efficiently. Clouds therefore collapsed into larger fragments, and the stars that formed were likely more massive, on average burning hot and fast. A giant born in such a clean medium would live briefly and die spectacularly, throwing out the first metals in its death and seeding its neighbourhood with the tools needed to build more complex generations. It is a pleasing story, and I think it's fair to say the broad strokes are on firm ground, but the particulars, how massive, how many, how quickly, remain a space for honest argument. The fossil record in the atmospheres of ancient stars in our own galaxy hints at those first supernovae, and telescopes aimed far back in time are beginning to see the edges of the dawn. Light from the earliest galaxies comes to us stretched by expansion until it pools in the infrared where our largest mirrors and coldest instruments live. When that light is split and examined, a familiar signature, the sharp cutoff in hydrogen's appetite for ultraviolet photons, slides redward with distance. By catching that edge and measuring how far it has moved, we place a marker on the map. This is how long the light has travelled. This is how young the universe was when the stars that emitted it lived and died. In recent years, we have been surprised more than once by the brightness and apparent abundance of small, early galaxies. Perhaps star formation was more efficient than we thought in those first halos. Perhaps dust and heavy elements appeared swiftly after the first detonations. Perhaps our models of how gas cools and fragments in pristine conditions need another layer of honesty. That is not a crisis. It is the thrill of discovery doing what it should, tugging the theory towards better shape. Those first stars did more than shine. Their light was energetic enough to prise electrons from hydrogen, turning a neutral fog into an ionized mist. Across the cosmic web, little bubbles of transparency expanded around young galaxies and quasars, then overlapped until the whole sky cleared. We call that long sunrise reionization. It is a phase transition written on a universal scale, before the medium between galaxies was opaque to certain colors, after it was clear. We can follow this change by watching how readily distant light is absorbed by patches of neutral gas along the way. We can also, and this is rather elegant, try to hear it by seeking the faint radio murmur of hydrogen itself as it flips the alignment of a lone electron. Tune to that line, and in principle you can make a three-dimensional film of the dawn, where the bubbles grew, how quickly, and under whose care. The first reliable frames of that film are still being exposed. Arrays of simple antennae listen patiently under quiet skies. Instruments spread across deserts and high plateaus search for a spectral dip that would betray cooling and heating in the early medium. Interferometers stitch together patchworks of red-shifted whispers. The data are delicate, everything between us and the signal is noisier and brighter, so the analyses are slow and careful. But each improved limit tightens the script. It tells us how many hot young stars must have been singing, and what kind of galaxies housed them. It nudges us toward a census of the sources that lifted the fog. In those first cities of stars lurked engines. We still struggle to explain black holes millions to billions of times, the mass of the sun already blazing as quasars when the universe was scarcely out of childhood. How did they grow so fast? There are two broad sketches, and they need not be rivals. One says, begin with the lightest seeds, black holes born from the collapse of massive early stars, and feed them greedily with gas pouring down the throats of small galaxies as they merge. The other says, under special conditions, when cooling is throttled and turbulence is kind, vast clouds can collapse almost directly into heavy black holes, providing a head start. The skies seem to contain both crowded nurseries and quiet corners. Perhaps nature took several paths at once. Jets launched by these young giants and winds blown from their bright accretion disks would then have battered their surroundings, regulating star formation and spreading the first metals further afield. Even at the beginning feedback, this courteous conversation between gravity and light was shaping the future of galaxies. Galaxies themselves are not solitary inventions. They grow by accretion, and merger along the filaments of the web, small systems falling into larger halos in an unending hierarchy. That process is messy, and beauty emerges from the mess tidal tails torn from graceful spirals. Starbursts ignited as gas is squeezed, globular clusters birthed in the crush, thickened disks and bulges left as scars of past encounters. Across time, the universal palette shifts. Early galaxies tend to be compact, clumpy, intense. Later ones, like our own, often settle into well-behaved disks with spiral arms that are more decoration than engine. The chemical abundance climbs steadily as generations of stars live, die, and return their enriched ash to the clouds. By reading those abundances, carbon to oxygen, magnesium to iron in old populations, you can reconstruct the tempo of star formation and the relative roles of different kinds of supernovae. It is archaeology of a kind the Earth cannot offer, a chronology 15 billion years deep preserved in starlight. There is a charming, almost domestic detail hidden in this cosmic grandeur. As galaxies light up the cosmos, they also create shadows. Dust made of the very heavy elements, those first supernovae return to space forms, grains that absorb ultraviolet and visible light and re-emit it in the far infrared. Entire star-forming cities can therefore be cloaked at shorter wavelengths and revealed only by their warmth. We need eyes across the spectrum, radio to gamma, to see the full truth. It is a reminder to be modest about what a single window can show. The universe rarely chooses to be simple. It rewards those who look twice. Now draw the map closer to home, because we are not exempt from this history. The Milky Way is a product of the same rules. Its disk, with its serene arms and orderly rotation, hides a rough youth. Streams of stars still wrap around it, ghostly ribbons, the shreds of dwarfs long since consumed. The bulge at our center likely remembers ancient mergers. The thick disk remembers heating events. The thin disk, where our sun resides, is a quieter, later chapter. Our star is a third-generation child, born from a cloud already salted with carbon and oxygen. The planets grew from that same enriched disk of gas and dust. Iron in our blood, calcium in our bones, phosphorus in our thoughts, each has a lineage that passes through the furnaces of stars and the detonations that ended them. When you hold a handful of soil to the light, you hold a time capsule, a memory of the first dawn encoded in everyday matter. As for us, we live in a spiral arm with a modest name, the Orion Arm, or Spur, where the night is gentle enough to see. The sun circles the center every few 100 million years, bobbing slightly up and down through the disk like a boat in a slow swell. We share this orbit with billions of companions and the occasional visitor from the halo. Our local sky is shaped by old supernovae that carved cavities in the gas and left behind shells and arcs. Even here in this quiet suburb of the galaxy, the echo of the cosmic dawn is present. The elements forged, then the structures assembled, then the rules drafted, then all continue their work. In a moment, I'd like to step from the galactic to the very immediate our star, our magnetic cocoon, and the thin blue film that keeps us alive. The same physics that lit the first beacons flows through the sun's cycles and the dance of Earth's field. The same interplay of order and disorder breathes in our weather. If we learn to read home with the same care we lavish on distant dawns, we discover a further marvel, that the path from cosmic birth to kettle steam is continuous, a single story told at many scales. Begin with the ordinary star that warms your hands on a winter window. The sun is not exotic by the standards of the galaxy. It is a middle-aged sphere of hot plasma, held together by gravity and balanced with exquisite poise by the pressure of light and particles streaming from its core. In the quiet center, hydrogen fuses to helium, releasing energy that takes a patient meandering journey outward, scattered, absorbed, re-emitted, until it emerges from the surface as sunlight. A handful of minutes later, that light arrives here, where leaves drink it, oceans shine with it, and our eyes and instruments turn it into meaning. But the sun is not simply a lamp, it is a restless magnet. Lines of magnetic field thread its surface, an interior like the grain in wood, twisting and kinking as gases rise and sink. Every so often the field tangles itself into knots and then lets go, releasing stored energy in flashes and storms. We call the rhythm of waxing and waning activity the solar cycle. Over roughly 11 years, sunspots multiply and retreat. The corona bristles or calms, and the wind that streams from the star, that ever-present breath of charged particles, grows more insistent or more polite. The solar wind is not wind in the way a sailor means it. There is almost nothing in it. You could scoop a cubic meter and count the particles on your fingers and toes. Yet it matters because it carries the sun's magnetic field outwards, shaping a vast bubble in interstellar space, the heliosphere that dwarfs every orbit and cometary path. Think of it as a magnetic cocoon, a moving, living boundary between the sun's influence and the gentler pressure of the galaxy's thin gas. At the front, where our motion through the local medium compresses the bubble, the wind slows and warms. Farther still, it yields to the outside. Spacecraft have touched that border and reported back a change in the song of particles, a new direction to the magnetic lines, the faint hiss of the galaxy louder than the whisper of home. Inside this great envelope, Earth has its own shield to carry. Deep beneath our feet, iron flows in the outer core, and that flow generates a magnetic field that reaches into space. It captures part of the solar wind and diverts it, shaping a teardrop cavity on the day side and a long tail on the night. Without that field, and without our atmosphere, the stormy moods of the sun would peel away our air grain by grain. With them, we are sheltered enough for water to stay liquid, for chemistry to play unhindered, for birds to navigate, and for compasses to point. Occasionally, the sun throws a tantrum, a flare bright enough to cast shadows in X-ray, or a coronal mass ejection, a billow of magnetic field and plasma hurled into the wind. If one of these clouds crosses our orbit and the orientations are mischievous, if the field carried by the cloud kisses Earth's field in just the right way, the two connect and energy pours into our magnetosphere. The auroral ovals brighten and widen, curtains of green and crimson flow, radio crackles, satellites shrug and adjust. Power grids feel a faint, insistent tug. Most days this is theatre grand, harmless, beautiful. Now and then, it is a lesson in humility. Our technologies are young compared with the old weather of space, and we are wise to study it with as much care as we lavish on ordinary storms. There is a quiet choreography to all this. The solar wind with its embedded field encounters the Earth's shield. The two fields exchange a little topology. Charged particles are guided down magnetic lines towards the poles. They collide with atoms of oxygen and nitrogen high in the sky. Those atoms reply with light. It is not magic, it is Maxwell's gift, the elegant unity of electric and magnetic forces turned into a nightly poem. You can teach the equations to a student and then take them to a dark field in the high latitudes and watch their eyes widen when the sky performs exactly as the mathematics promised. Above the clouds there is another player, the ionosphere, a layer where sunlight strips electrons from atoms during the day and they rejoin at night. It reflects and refracts radio waves bending signals over the horizon. The aurora stirs it, solar flares wrinkle it. The quiet cycle of the sun lifts and lowers it like a slow tide. Mariners once learned these moods by experience. Today, a web of instruments listens and models and predicts. Space weather is now a forecast, not a surprise. I'm often asked whether the sun's changes steer our climate. The honest answer is that the star matters profoundly in the general sense. Without it, there is no climate at all, but that the specific flickers of its cycle are gentle compared with the effects we are now imposing upon the atmosphere. The 11-year breathing of the sun is worth tracking. It paints delicate patterns on the upper air. It nudges the stratosphere. It speaks softly to ozone and winds. But the great changes down here, temperatures rising, ice retreating, patterns of rainfall shifting, are driven mainly by what we release and how we use land and water. This is not the place for alarm. It is the place for clarity. The physics that explains aurora and dynamos also explains how greenhouse gases trap heat and how energy flows through air and ocean. The equations do not care for politics, they care for balance. Stand then somewhere you like on this planet, on a cliff above a grey sea, in a city street, washed with rain, in a field with your breath steaming in the morning, and you can feel the whole chain at once. Deep below you, iron flows and turns. Far above the ionosphere scintillates. Farther still, the heliosphere rides the weak currents of the galaxy. The same sun that fused helium into existence warms your face. The same laws that shape the dark rings around black holes guide electrons that draw a thin line of green across the northern sky. The cosmos is not a collection of separate rooms. It is a single house with many windows. I like to think of Earth as a lucky eddy in a long river. Energy pours from the hot center of a star into the colder reaches of space, and in the gentle gradients and swirls between here and there structure blooms. Our weather is one such structure. So is the pattern of ocean currents. So are forests. So is a thought. The arrow of time pays for them all, and the sun is the coin. When the cycle of activity rises, the space around us is more animated. When it falls, the sky's theatre quietens. Through it all, the steady output of light continues, and life takes its dividend with patient hands. We have, over the last century, taught machines to be curious on our behalf. Balloons sounding rockets and satellites now watch the sun constantly. They weigh flares, taste the wind map, magnetic loops, and follow the rise and fall of storms across the corona. Other craft feel the wind directly riding the inner system like weather buoys. Farther out, quiet explorers drift at the edge of the bubble, counting the passing of cosmic rays, timing the gusts. Piece all of this together and you have a living portrait, a star as a system, a planet as a shielded garden, a bubble as a moving frontier. In a moment, let's turn our curiosity back to ourselves, to the craft of knowing. We have wandered from black holes to kettles, from first light to aurora, and the thread that binds it all is a method measure: compare, doubt, refine, and share. I'd like to end our journey by walking that method into the far future. What becomes of stars and planets, of black holes and light when the fuel runs low? How does a universe age? And what kind of poetry remains when the lamps dim? There is a virtue in astronomy that is easy to miss amid the fireworks' patience. We have learned to take a handful of principles, gravity, thermodynamics, quantum rules, and allow them to run for very long times. The method is modest. We do not claim to know every detail of tomorrow's weather in a far-off galaxy. We ask instead what must happen if the same laws that work in kettles, clocks, and clouds continue their quiet governance. So when we ask how the universe ages, we are really asking a humbler question. If we let known physics do its work for a very long while, what story does it sketch? Begin with stars, those steady engines that have illuminated the cosmic Middle Age. Not all stars live at the same pace. Big ones race through their fuel in a few million years, burning hot and dying young. Small ones, the reddish dwarfs that make up the bulk of the stellar population, sip their fuel with exquisite thrift. They mix their interiors so thoroughly that almost all of their hydrogen can be used, and so they may shine for trillions of years, thousand upon thousand of times the current age of the cosmos. For most of the universe's future, the night will be lit not by great blue beacons, which are rare and brief, but by small, steady embers hanging on with stubborn grace. Our own sun sits in the comfortable middle. In a few billion years, it will swell into a red giant, shed its outer layers, and leave behind a white dwarf, a cinder the size of the Earth, held up not by heat but by the quantum reluctance of electrons to share the same space. White dwarfs are not dead, they are quietly cooling. Some crystallize from the inside out, their carbon and oxygen forming a sort of diamond lattice, and as they freeze, they release a whisper of latent heat that slows the fade. Given time enough, even that glow will fail. The cinders will dim into black dwarfs, cold, dark remnants with the mass of a star and the temperament of a stone. Galaxies evolve as their fuel is spent and recirculated. For a while, gas flows into new stars, then supernovae and stellar winds blow some of it back into space, and the cycle repeats. But there is leakage at every turn. Some gas is heated and lost to a galaxy's halo. Some is locked away in faint, long-lived stars and brown dwarfs. Some is swallowed at the centers by black holes. Over vast stretches of time, the easy reservoirs of star-making material are depleted. Star formation slows, then dwindles, then ceases. The grand fireworks of the early universe give way to a quieter era of red dwarfs and afterglows. On the largest scales, the expansion matters. Space is not merely getting larger, it is accelerating in its growth. Gravity still binds what is already close and tightly knit. The small group of galaxies we call local will remain a single island, but distant shores will slip beyond reach. In the far future, observers living in our merged home galaxy will look out and see only darkness beyond a halo of ancient stars, because the light from other islands will be stretched thin and stolen by the expansion never arriving. It is not that those galaxies have vanished. The universe has simply placed them beyond conversation. The cosmos becomes archipelago, scattered silent estates, separated by ever-deepening seas. Within each island, the dance continues. Orbits shuffle. Stars pass and tug and occasionally nudge one another from their paths. Some are flung into the dark to wander as rogues between galaxies. Others are drawn towards the center, where a supermassive black hole waits. Collisions between galaxies become rare, then essentially finished. The remnant is likely to be a calm, swollen system with little gas, many old stars, a massive black heart, and a long memory written in the motions of faint streams. Planets persist, but their stories are domestic and intricate. Worlds around red dwarfs may orbit for far longer than any human language could describe. Some will be shepherded into tighter paths. Some will be cast off into interstellar cold. Some will spiral into their embers under the slow drag of tides and radiation. The romance of warm oceans and soft skies is not promised for the entire span, but neither is it denied. There will be havens and endings scattered across unimaginable ages, many never witnessed, most never recorded, all permitted by simple rules. Black holes rise paradoxically as the light fades. They are efficient sinks for accident and debris. Through dynamical friction and occasional feasts, they will grow, especially the giants that sit in galactic centers. When little is left to eat, they will wait. And here the most patient music of all begins. A black hole is not entirely black when quantum mechanics is invited to the horizon. It radiates faintly a thermal whisper whose temperature falls as the hole grows. For stellar mass holes, that whisper is so cold as to be meaningless. For galactic giants, it is colder still. But let the clock run to numbers with more noughts than you care to count, and the accounting changes. Even the largest sink will leak very slowly, losing mass until in a final modest sigh it evaporates. The last acts of the universe may be played on that stage long winter, punctuated by rare soft fireworks. All of this rests upon extrapolation. We can be honest about the uncertainties. If protons decay a possibility not forbidden by some versions of the grand unifying dreams, then matter itself is less durable than we suppose. And the path to quiet comes sooner, with atoms gently unthreading into radiation over timescales, vastly longer than any star's life. If the dark energy that drives expansion has a more mischievous character than a simple constant, if its pressure grows with time, then space could stretch to the point where even bound structures are pulled apart. A dramatic ending sometimes, sketched as a great ripping. The present evidence favours no such drama, but science is a ledger kept in pencil. We write our best accounts and remain willing to edit. There is another more subtle possibility whispered by particle physics, that our vacuum, the placid stage on which the play unfolds, is not the lowest possible state. If so, it could in principle change rolling or tunnelling to a truer calm, rewriting the laws as it goes. Were that to happen, the change would race outwards at nearly the speed of light, and there would be no time to worry about it, nor any meaning to worry with. This is not an invitation to gloom. It is a reminder that the deepest questions are still alive. The prudent response is not fear, but curiosity, and the proper instrument is a better collider and cleaner theory. You might ask, as one should, what poetry remains in a universe heading towards thinness and quiet. The answer is that the poetry was never in the fireworks, it was in the comprehension. To know that stars are possible at all, to connect the aurora over a northern sea with spirals of charged particles and field lines drawn from a hot bright sphere, to read the freckles in the first light, and see in them the seed of your own breath. That is the meaning we bring. The future does not rob that meaning, it deepens it. It says that fleeting things can be honest and complete. A star's life is not less beautiful because it ends. A civilization's questions are not less noble because the answers lead to silence. We are each of us temporary arrangements of atoms on the slope of time, and yet for a while we can hold the universe to the light and make sense of it. That is miracle enough. Stand outside on a cold night and listen. The sky does not speak in words, but it keeps its promises. The laws do not waver between your cup of tea and the great black rings around distant hearts. In that constancy there is comfort. The past will always be a place of dawns, the present a workshop of ideas, the future a long exhalation into peace. We are here now gifted a brief interval in which to learn to share and to be astonished. In a moment I'd like to gather the threads, not as a summary, but as an invitation. We have wandered from the first light to the last by way of storms and shadows, rules and riddles. Before we leave the theatre, let's sit for a while with the simple fact of our good fortune to be awake in a universe that can be known, and to know that the knowing is never finished. It's reasonable to say that the most valuable thing we've learned on our journey is not any single fact about black holes or dawns or distant weather, but a habit of mind. We ask questions that are just within reach. We build instruments that stretch our senses. We compare what we expect with what the universe delivers, and when the two disagree, we change our minds. That is the quiet engine that carried us from the first light to the last, from kettles to quasars, from aurora to entropy. The details will evolve, new particles may be found, fresh maps of the early sky will arrive, gravitational observatories will deepen their hearing, but the method remains sturdy and humane. Stand for a moment in the doorway between those worlds. On one side there is the practical engineers hanging mirrors on silk threads to hush the Earth's tremor, coders teasing patterns from noisy data, technicians cooling instruments to a hair's breadth above absolute zero, so that a single photon can be counted with dignity. On the other side, there is a patient philosophy. We admit what we don't know, we sketch possibilities, we let nature answer in her own voice. The bridge between the two is curiosity coupled to discipline. Without discipline, curiosity frays into stories we tell ourselves. Without curiosity, discipline hardens into ritual. Together they become a way of seeing that is, I think, our finest inheritance. As we walked, a few themes returned like friendly constellations. One was scale. Tiny ripples, 1 part in 100,000, seeded the architecture on which everything rests. Small imbalances in early chemistry led in time to stars that fused carbon and oxygen, to planets with iron cores and blue skies, to beings who ask why. Another theme was unity. The same equations that shape the ring of light around a black hole also describe the glow of an aurora. Maxwell's neat handwriting on a chalkboard flows through the tails of comets and the needles of compasses. Thermodynamics sets the arrow for kettles and for galaxies, for the cooling of dwarfs and the settling of minds after long days. When you speak that language honestly, the universe replies with consistency, which is a kind of kindness. And then there was humility. We named dark matter and dark energy not to claim understanding, but to hold our ignorance steady enough that we could approach it. We learned that horizons hide detail, that some information is not ours to enumerate, that even our best pictures of the beginning and the end are sketches made in careful pencil. We discovered that our star is ordinary and our place unexceptional, and out of that ordinariness came a more remarkable revelation, that meaning is not granted by centrality. You can be a small creature on a small world, in a quiet arm, and still find the laws that govern everything. That is to me a better kind of significance earned, not assumed. If you wanted a single object to carry this whole lesson, you could do worse than a map. Think of the sky as we found it at the beginning of our species, a dome of mysterious lights. Then think of the map we hold now, background, ripples, measured to exquisite precision, the scaffolding of dark matter inferred by the bending of that light, the distribution of galaxies marked by the faint crest of ancient sound, the births and deaths of stars counted by their colours and their spectra, the rings and ovals of giants read as seismographs, the atmospheres of other worlds caught in transmission as they cast their small shadows. No mythology could be more generous than a reality that allows so much to be learned with so little, just photons, just patience, just a willingness to be wrong. Of course, there are frontiers where the ink is thin. The identity of dark matter remains open. The nature of dark energy, cosmological constant, or something with a pulse we do not yet know. The quarrel between quantum theory and gravity, which whispers at horizons, and in the first instant continues. The rate at which the universe expands today is a bone over which honest dogs tug. Somewhere perhaps a particle waits at a mass we have not yet reached. A symmetry waits to be broken in a way we had not considered. A mathematical idea sits unannounced in a student's notebook, patient and inevitable. That not knowing is not a gap to be feared. It is an arrow on a signpost reading this way. If I were to leave you with one more picture, it would be of the future observers looking up from our island. Call it the merged remnant of our local group, long after other galaxies have slipped beyond communication. They might see only the stars of their own estate and the cool relics of those that have already lived. The background glow will be stretched to wavelengths that no simple instrument can catch. The clues we now use to reconstruct our history will be faint or gone. And yet, armed with the same habits we've practiced, measure carefully, compare honestly, argue politely, they will still be able to build a working cosmos. Gravity will still bind, light will still carry momentum, atoms will still protest when squeezed into the same state. From such threads, a tapestry can be woven again. The universe is not just knowable, it is re-knowable. There is comfort in that. We are temporary, but our way of finding out is robust. Children not yet born will ask old questions with new tools and will receive answers we cannot guess. Some will be prosaic and precise, others will be shocking in their simplicity. And every so often a discovery will revise something we thought secure, and the revision will make the world larger rather than smaller. That is how it has always been, from the first careful charts of the wandering planets to the first whisper of space-time ringing after a collision in the dark. Where then do we stand? On a small planet, in a calm interval of a long history, under a star that rises every morning. The air we breathe was supplied by ancient leaves and old oceans. The iron in our blood was minted in explosions we have not yet seen. The calcium in our bones condenses the story of stars into the mundane strength that lets us walk. We are woven from the same rules we sought to understand. You can go outside on any clear night, look up, and know that the glow between the stars is the oldest photograph in existence, that the ring around a black hole is a portrait of geometry, that the green ribbon over a northern sea is a poem, written by electrons, that the planet you cannot see around a star, you can barely name, has an evening sky with colours we have already measured, and so it falls to us to be careful with this good fortune. Curiosity is not guaranteed, it must be nourished. Institutions that protect patience and precision must be tended like gardens. The same light that shows us exoplanetary weather can be used to illuminate our own choices. The same discipline that taught us humility before nature can counsel humility before one another. If there is a moral in the physics, it is simply that truth is indifferent to preference, and yet our preference for truth can make a civilization gentler and more durable. Now let the theatre go dark. The instruments rest, the maps are folded. Somewhere a detector will twitch in the night as another pair of stars collide. Somewhere else, a small telescope on a quiet hill will watch a distant planet take a bite from its star and send back, hidden in the starlight, the faintest taste of an alien evening. The sun will rise on schedule. The kettle will sing, the arrow will continue its patient descent, and we will go on asking questions, because that is what it means to be at home here. Thank you for walking with me from first light to last, from rings to rivers of time. If you take anything away, let it be this: the universe is understandable, and the understanding is ours to share. The rest is practice, gentle, honest practice under an old and reliable sky.